Mm, Hi everyone. Uh, today, today I'll be just talking about one of the cool projects I did in my class. We all took operating systems class in our bachelor's and in our master's, but uh, in my current for my master's we learned operating systems in a different way. So I'm gonna give you a brief introduction of why do we do scheduling in operating systems, and then we'll go through the project that I did, which visualizes some of the scheduling algorithms most frequently which are used. So, so why do we need, the first question we need to ask is, why do we need scheduling, right? So, we need scheduling so that like we want to run multiple processes. We want to finish maximum jobs, good latency, like there is no hanging of the system and such things. And you also want, like wait time. You want to minimize it. And also like you want to like every CPU has a clock, right? So for each cycle, you wanna come you want to do max work. And although, so you can call all of these as, the goals of scheduling. So in practice, all these goals conflict with each other, and but you always have to compromise depending upon the requirement that you have. See, um, and like the final thing is like you have to be fair. Like each process should have some CPU time. You can't put a job waiting for the CPU to be run on it for a very long time. That's not practical at all. So these are all the like the goals of doing scheduling. And as you all know, like each process goes through some states. Like when a process is created, there is a new state, and when it is ready to be executed, then it goes to ready state, and while it is running, it is in the running state, and if it finishes running, it goes to exit. And if some interruptions came in between, then you wait, and during the waiting, if you can do some IO bursts, and then again when it is ready to be executed, it goes to the ready state. So these are all some of the states um, of a process before it is fed into the CPU. So so some of the basic scheduling algorithms which I'm gonna show you what I did are, first FCFS. So it's simple, like you have a queue, you have job 1, job 2, job 3, job 4. You start with job 1 and you execute it until it finishes, and then you go to job 2, then you go to job 3, then you go to job 4. So It's a non-preemptive algo, you know. So it's not that good of an algorithm where you have to wait for one job to finish. Let's suppose say that one job went to the waiting queue, then all the jobs have to wait for this particular job to finish, and you're minimizing the throughput of your CPU. What does it mean by throughput? Throughput is like maximizing the job done per unit time of the CPU. You're not doing it, so it's not an ideal. Round robin. So let's suppose say there are four jobs. CPU starts one job. Let's hit 5 millisecond, 5 millisecond, 5 millisecond, 5 millisecond. CPU executes each job like they are in a queue from the queue, one job at a time for 5 milliseconds. It doesn't have to be 5 milliseconds, but for simplicity and clarity, I'm telling you like the CPU goes through all the jobs 5 milliseconds until all of them are finished. It is also it is better than first comes first served, but at any given point of time, the jobs are being sent into the wait queue, and you're like you're increasing your unwanted calculations, the burden on the CPU for each 5 milliseconds, you know, and priority based. So it's a preemptive algorithm. What does it mean? So let's suppose say you have four jobs with priority, I don't know, four, three, two, one. So job one arrived at, I don't know, 1:20 p.m. This one will arrive at 1:21, 1:22, 1:23. So what does it mean? Like, so uh, at 1:20 p.m. you only have job one, so it will be executed for 1 minute. But at 1:21 you have a job with higher priority. So the CPU stops executing job one and goes to job two, and it will be executed for until job three comes in. And then job three executes for 1 minute until job four comes in, and CPU executes job four until it finishes. So all these scheduling algorithms have their plus and minuses, but priority based is completely fair. Like let's suppose say you are using a Word document and you have opened multiple, you opened Chrome and all these things on your CPU, but right now you're only using Word document. You're editing some Word. So what CPUs does is it puts Word document as the priority number one, and it keeps on executing your Word document until you move on to the Chrome. In that case, it will stop the Word document. It stores the whatever the state you have left it, and keeps on executing, the remaining the Chrome application. So that's that's one of the benefit of priority based. But in like I said, every algorithm has its pluses and minuses, and in priority based, there might be a situation where job one might never get CPU time again. You have to balance all these things. So the other thing is MLFQ. This is called multi-level feedback queue. You can say let's let's suppose say you have three levels of queues in your new state. So this queue, Q1 is gonna be priority based. Q2 is gonna be, let's suppose say, round robin, and Q3 is gonna be FCFS. So in multi-level feedback queue, you have multiple levels of queues. So the highest priority, it doesn't have to be like from, okay, so jobs are selected from Q1 for CPU execution, and they are executed for a certain amount of time. So let's suppose that there is job 1, job 2, job 3, job 4. So job 1 is executed, consider 1, 2, 3, 4 as the priority. Job 1 is executed for like, I don't know, 20 milliseconds, and then job 1 will be sent from Q1 to Q2, and the priority of job 1 will be reduced by some amount. Since already job 1 has CPU already, you want other jobs to find CPU too, and when jobs keep coming in, Q2 will be filled out. Job 1 comes here, job 2 comes here, job 3 comes here, job 4 comes here, job 5, job 6, job 7, job 8. So we don't have anything empty in Q2. Then it will go to Q3, job 5 and such. So here, when when all the jobs in Q1 start becoming empty, it starts looking for jobs in Q2, and you can also, like, after each 5 seconds, since Q3 is the you know lowest level of queues, it's very hard to bring jobs from Q3 and to Q1, because every job which is selected to CPU comes from Q1. So after 5 seconds, what you can do is you can take out one job and you put it into Q1. It doesn't matter what its priority is. You just put it there and wait for Q1 to select this particular job, you know. So in multi-level feedback queue, you can implement first come, first serve. You can award and you can punish a job, and you can reduce the priority. You can upgrade the priority. So this way you ensure that all the jobs in your queues get CPU time, and they will be executed in the jobs will be executed time by time. So these are some of the basic things that I wanted to cover before I show you the code of what I did. So now let's going back to my program. So what I did, let me go back to, let me explain. Before I show you the code, let me talk about what I did in this. So in this project, what I did is, like, I have mimicked scheduling, you know. So for that, what I did is I wrote a main function, uh, where you run infinite loop and you receive jobs from an API call in the form of a data structure, like job has, CPU bursts, IO bursts. Each process has some CPU bursts where it is run on the CPU and where it use IO devices to show some outputs, you know. So this is not an actual jobs per se. All you do in a data structure, you're creating, you know, data for that particular job, just with CPU, how many CPU bursts it have, and each CPU burst, time. Let's suppose say CPU, there are five CPU bursts, there will be five times, you know, and there are IO bursts, times one, two, three, four, five. The first CPU burst is going to be one, the second CPU burst is going to be one and two. But what I'm saying is, until you at the end of the burst, you have you have a finished, or you can say minus one. That means the job has been executed, it completed all its bursts. Same with the IO. At the end of the list, you have -1, telling your program that there are no more bursts to be completed, and the job continues to be in the waiting state until all of the bursts of that particular job have been completed. Like, for example, say job 1 has 2, 3, 4, -1 bursts. So, and each of these bursts has a timestamp, like suppose say 120, 125, 120, I don't know, 130, 150. So until 1:50 p.m., this job will stay in, like, the first burst will be completed in 2 minutes, so 122. The second burst will be completed in 3 minutes, 128. It goes to the waiting state and it comes back to the ready state again. So, it's a dynamic way of what I did. So, so my loop runs forever, and for each iteration, I'm considering that as one clock tick. Each loop iteration. So for each take, the maximum I can do is complete 1 unit of the time burst from any particular burst of the item. And and then what I did is I calculated um, waiting time. I calculated the output time. The formula is gonna be average job done time divided by average waiting time into 100. Uh, Average waiting time, and you can see I have totally visualized whatever I did in the program, and you can see them in the output, like which one is, like, the states, and you know all these things: the robot time, waiting time, start time, bursts left, and all these things. I have shown them in a table for you, for you guys to understand. So Let me go to the program now. So this is our main program. I wrote everything in Python. So these are the like the base model for we are getting the jobs in data structures from an API. I didn't implement the API, my professor did, but the API, this is the data structure. I tried to match the data structure which I get from that particular API. So job ID, arrival time, bursts, priority, ready wait time, IO wait time, run time. So you need like for each job you need to update this ready wait time, IO time to calculate some of the basic, you know, statistics you need. What all these things. So fetch bursts basically what it does is like from the API it fetch bursts for each job, but before fetch burst is called from this particular function. It you do like you fetch mm, like you fetch the details of that particular job for each iteration of the loop, you know. So this, like I said, this is where so this is where I run my loop. It has its own current clock tick. You get the jobs, you fetch unique jobs at each clock tick. Like clock tick, you see like new jobs are coming in for that particular time. And yeah, then put them from whenever they come from new, then you send them to the ready queue and you select which algorithm you want to run, and then you visualize whatever you did, you know. So one more important function that I have is the controller. So what I do is like sorry. So what I did is like what I'm trying to do is controller is whenever you're running the while loop, it runs so fast you won't be able to pass your results and see it. So what I did is like, you know, in the script I send a sig kill, kill command for that particular main Python file that I run. But whenever I receive, you know, kill command from here, my main function, what it does is it receives that signal. It receives that signal here. Sorry, not here. Mm, signal handler. You know, from the OS, from SIG user when you send that signal, the kill signal, it puts that your job in sleep mode until you press one more button R to resume, P to pass. You know, that's what you know. That's what I try to do. I'm sorry. So yeah, the scheduler is where you implement different algorithms. Like I said, the first come first served. This is the first come first served. You have the jobs. You know, from CPU you reduce the burst time for each burst you receive, uh, and you keep on updating them. You calculate the total time run for that particular job. So that is also the CPU busy time, and whenever it goes to the wait time, you calculate the wait time. The same, this is the priority based, and the same when you go through the code, you will be understanding like what I try to implement. This is the first MLFQ, uh, where I implemented a mix of priority based, round robin, and you know mm, first come first served into one algorithm so that no jobs is left out. So this is how you run this particular file. Uh, the config.json. So as you can see, this is the configuration file. You tell the API like this is this many jobs I need, and your API, you know, creates a data structure with these requirements and you know the time interval. Like it's not the actual jobs. I'm just telling the I'm creating a data from this configuration like uh, let's suppose say minimum jobs 5, maximum jobs 5. So 5 process jobs will be created. Minimum burst 3, maximum burst 3, 3. There will be 3 bursts, and minimum job interval 5, maximum job interval 6. So at each 5 clock ticks, you get a new job. The burst type ratio is like 0.5, which means let's half jobs will be CPU jobs, half jobs will be IO jobs, you know. So minimum CPU burst interval is 10. So each burst will be of interval 10 second, 10 clock ticks. IO is also 10 clock ticks. And minimum time is TS interval means like so like so the burst interval, this is the clock tick for the umbrella. So you receive jobs for each five ticks, and you receive bursts like let's suppose say one job has 5 bursts. You receive the burst at an interval of 3. So at each 3 clock ticks, you get the new burst for that particular job. So it's a cool way to visualize your algorithm. So let me run it. So here I'm just running the round robin for simplicity. So as you can see, these are we received a job 1. It is going from one job to the other. You keep running. Jobs are going from ready to running, and then they are going to new. When they arrive, they go to new. Then they go to running. Sorry, ready. Then they go to running. And as you can see, at each clock tick, it is either using the CPU or it is either using IO, and uh, it has completed all the jobs. You can see the final statistics. Average turnaround time 46:20. Average ready wait time. The ready wait time, like the number of jobs waiting in the ready queue, and the number of jobs waiting in IO, and the total. See, even with running like the round robin is only have a CPU utilization of 54%. So half the time the CPU is being idle, even though we try to, you know, use the CPU to the maximum capacity, you know, and we can also run FC FS. The seed is just a unique ID number that you give to the API. You can wherever when you stop running your main function with the seed number, you can start where you left off. It remembers like how many jobs you have completed, and so here we have two CPUs and here we have four out IOs. So as you can see, I didn't just use one CPU and one IO. We have multiple. So even with IOs and even with CPU, we did. So whenever a CPU is available, I was able to assign that to a job. So it's a complex project. Like we had multiple CPUs, we have multiple IOs, and we are constantly trying to utilize every available device we have. So, you know, we are running first come, first out. So, job one is arrived. It is running. It whenever it finishes burst, it goes to the waiting. And if it is doing IO, it goes to the IO queue. When it is terminated, it goes to the terminated queue. So that's it, sir. That's what I did. Mm, I did more of it, but if you like my project, you can contact me. We can talk more about it. Thank you.